Okay, g'day everyone. In this video I'm going to be covering how a one-way ANOVA is performed, and from this video I'll then do a two-way ANOVA, and then I'll go into regression, and that should catch us up to exactly where we are at the moment. Okay, so what a one-way ANOVA is, it's a way of being able to, let me just quickly kill these, apologies for this. The data that I'm going to be working with in this case is the data for the for Prac 7, which is, I believe, it's definitely this one. There may be another data set that you have to use, is the candle data. And what they've got in this situation, you'll see if you've opened that in front of you, you don't have this column. I'll show you how I got that column in a second. But what they were looking at is they were trying to see the different variables associated with, for a given candle, like say you think of like a birthday candle that go on top of the cake. They wanted to identify which variables impact upon how fast the candle actually burns. So what they did is they recorded for different candles that come under different classifications, which I'll go soon. They lit it on fire. They waited for a set period of time. Then they extinguished the flame, and then they would measure how much it's actually changed. So what we see here in terms of the variables is they looked at different packets. I'm not sure if the different packets refer to different brands. Let's just assume it is brands. They then looked at to see whether or not the color of the candle had an influence, the initial weight of the candle, and then how it was burnt. So you think about the 90 degree, that's the same as like perpendicular, so straight up on top of, say, the cake, for instance. That burns at a completely different rate than if you were to put it on an angle at, like, say, 45 degrees. So they tested it for different angles. I think the two angles that they looked at was 90 degrees and 60 degrees. They recorded the initial length and they recorded the end length. And then obviously the key thing I guess they were looking at, the key thing I believe they were looking at in this case was identifying how that impacted on the total amount that was burnt. So we're not so much, well, we may depending upon the test, but in this case I'm not really bothered about the initial length or the end length. The key thing that I'm looking at is just overall how much is burnt. Now the initial length and especially the initial length may play a massive role, but in this case I'm just going to assume that the diff is all we're interested in. Now if you want to know how to calculate that, in terms of naming it, you just double click on the cell and you can type whatever you want. So I'll just call it a diff in this case, and to calculate this, as I said, it's the difference between these cells. You go to calculator, it says store the result in, and you'll just type in their diff. It should come up in these options here, and then the expression, how we get that, is just equal to the initial length minus the end length. Okay, and it'll populate those cells. Okay, so what we want to do is we want to see whether or not there is a relationship between, in this case, difference and one of the categorical variables. So in this case I'm going to be working with color, but you could equally do this with packet or angle if you wanted to, and then you'll see in two-way ANOVAs that we can actually do multiple in one go. So how do I identify if there is a relationship? Now, when I state relationship, that can be a bit of an ambiguous term in statistics. Relationship is defined by the test. So in this case here, what we do in a one-way ANOVA is we go, okay, here we've got data for a whole, in this case, we've got data that refers to multiple different cases of a categorical variable. So what I mean by that is, these different values here are also correlated with, well, not correlated, but they're matched with different colors. So this variable here refers to pink, this one here refers to white, and so on and so on. So what an ANOVA does, it says, okay, when we've got a response variable, and the response variable always has to be numerical, so it's numerical in this case. If we take a categorical variable, now before I go any further, I just want to quickly state, you'll notice that in Minitab, you'll quite often see the terminology of factor and level. Now what a factor is essentially a categorical variable when we're talking about a one-way ANOVA. So this is the response variable, the categorical variable is the factor, and then the different values the categorical variable can take, or the factor can take, in this case pink, white, yellow, blue, and so on, are referred to as the levels of the factor. So just summary, response variable is the numerical, which is diff, the factor, or the categorical variable, is color, and the factors levels, or the categorical variables values, are pink, white, yellow, blue, blah, blah, blah. So when you see that in Minitab, I'll do my best to constantly remind everyone, but if I forget, that's exactly what they mean. So anyway, what an ANOVA does is it says, okay, what I'm going to do is I'm going to take this large data set which includes everything, and I'm going to split it up based upon the different colors. So I have different sets. essentially. So the first set would involve all the values for the pink, the second set will involve all the values for the white, the third would be all for yellow, and so on for the different colors. It then says once I put them out into their separate bags, if you will, I can calculate the means for each of them. So I can get the means for the pink, the mean for the for whites, mean for yellow, mean for blue, and so on. So I get a different mean for each of those. And what we want to identify is, are the means equal? Now, if the means are equal, then that means that separating them out, excuse me, separating the difference out based upon color isn't really showing an effect. I mean, if you were to separate them out and say, for instance, okay, let's go through the case of they're equal first. I apologize for going off on tangents here. Let's just say that you found that the mean was like 70, this was 68, that was 73, this was, you know, maybe 70.1, and so on and so on. If you find that by separating them out based upon, in this case, the different level values or the different colors, then that means it's not really changing anything. It doesn't affect the mean difference time. They're all relatively equal. Now, if I was to separate them out and you found that the mean for pink was 10 and the mean for white was 100 and the mean for yellow was 70, then in that case, by separating them out based upon their different colors, when I calculate the means for those different colors, it has a massive impact. And so if it has a massive impact, we say that it has a relationship. But remember, in this case, we're defining relationship as saying that those means are equal. It does not mean absolutely there is a definite relationship between the two. It just says that when we separated them out based upon colors, when we calculate the means for the different colors, they appear to be all equal, and therefore it's not having an effect. If you separated them out and they had very different values, then you could say, yes, by separating it out, it has very much influenced the different means, and therefore if we have different means, then yes, there is some relationship between difference and color. We just need to be aware of what type of relationship we're talking about, because I could equally perform another statistical test under the same framework of I have a numerical response variable and I have some categorical variable, and let's just say the first test, so the One-Way Anova, says there's a relationship, and then I go into the second type of test and it says there isn't a relationship. Well, when you're using relationship in those two different terms, they mean different things for different tests. So when you get a relationship positive, so to speak, reading in one test, and you get a negative in the other, that just means that based upon the first test and the way that it defines a relationship, we've got a relationship. But then in the second test, in the way that it defines a relationship, we don't have a test. So don't think that when you say relationship, it's this uniform term across, and it means exactly the same thing across each of the different tests. It is all based upon the mechanics of each individual test. Okay, so what I've written up here is basically just a summary. I'm going to release this with the video when I put it onto the Blackboard page, and I've sort of filled in a little bit, and I'm going to be filling the rest as we go through this. Okay, so as I said, here we wish to analyze the relationship between the diff in the candle length and color. So just going back, we're analyzing the relationship between this and this. As it says, as diff is a numerical variable and color is a categorical variable, we can apply One-Way Anova. You don't have to include this sentence. It's just generally a nice way of introducing it, because then it tells the marker, which more than likely I'm going to be one of the markers, is saying that you've identified the variables and you've identified that you can apply this test to it. So it tells the marker, if you make a mistake from here on in the way you apply the method, at least we can definitely say you identified the situation, sorry, you identified your variables correctly, and then you identified what test you can use correctly as well. And that's a big part of the marks. Okay, so this is just a little bit of background information. You don't have to include this if you don't want to. This is just more for an explanation for when you're looking later. So One-Way Anova assumes that each of its factors levels are normally distributed with equal variances. So let's go back and have a look to say what that exactly means. That means that if we separate it out based upon color, so if we just got all the pinks together, so to speak, and then we were to perform, if we were to generate a histogram based upon that, we'd want to see that that's normally distributed. The same is true for the white, the same is true for the yellow. So for each of the factor, remembering again that the factor is the color in this case, its levels, pink, white, yellow, etc., sorry, are normally distributed. So each of them have a normal distribution, and that they each have equal variances in that normal distribution. That's a massive assumption of this, and that's something that we're going to go into later as well. So don't worry if you think that I'm just typing it up here and that's all I'm going to say of it. We're going to test that. Okay, And so here we are testing whether the factor color has an influence on the mean response value diff. So we're seeing if we separate it based upon colors, does that change the mean response value? So, and again too, this is just what we've already gone through. Here the response variable is equal to the difference, the factor is equal to color, and then the different values that the factor can take, or its levels, is blue, pink, white, and yellow. And it says, and also we are testing how the color affects the mean difference. We are testing how the color affects the mean response diff. It's a bit of a, yeah, I know I'm sort of repeating myself a little bit. Anyway, we've got two different ways of writing the null and the alternative hypothesis as we have here. Both are equally valid. If you're unsure about, I mean, as long as you write it correctly, it doesn't matter which one you use. But if you're unsure, you can include both. You're not going to be, you're certainly not going to be marked down if you were to include both. But essentially, we don't want people including things or writing things in these reports unless they're going to talk about them. So if you're not 100% sure, then this is something that obviously you need to talk to either your prac supervisor or someone within the MAB 233 admin team, so to speak, and they'll help you with formulating it. But if you want to include both, you can include both. So as I said, one way of writing it is the mean, in this case, difference, so that's what we're measuring. The mean difference is the same for each color. And then the alternative is, if the null is that they're all equal, the alternative is at least one is different. So at least one mean different is different from the other. The second way of writing that, which is an exact same translation of what we've got here, is we're testing this by saying the mean diff is the same for each color, is the same as mean blue is equal to mean pink is equal to mean white is equal to mean yellow. And the alternative is at least one mean is different from the others, or at least one mean is not equal to another. Okay, so that's what we need to test. The first thing we need to do is we need to get the results from the ANOVA. Okay, so let's go into Minitab and let's do that. So we go to Stat, ANOVA, One Way. In the response variable we have diff, in the factor we have color, so it'll be selected from here. If we go into the graphs, I can't remember exactly what this is by default, but this is what we want to see. We just want to have these two highlighted. I think none are highlighted by default. So just check those, click OK, click OK. Got a few graphs to come out. I'm just going to put them to the side for the moment. We don't need that one for this. And the first thing that we want to do is we just want to get a copy of this. So we're going to right click, send lines to Microsoft Word. I hope it went exactly where I wanted to. So yes. So here, so what we've done is we've what we've done so far is we've talked about the situation, we've talked about what tests we're going to be doing, we've then formulated, the null and the alternative hypothesis, we've gone into Minitab, and we've got the output. So I hope you can read this. I'm sure if you if you to zoom in, you should be able to see this. So the key thing that we're looking at to start off with is this p-value that we've got within here. And see, I've got, let me just get rid of that. It must have brought it over twice. Sorry about that. Okay, so the first thing that we need to talk about is this p-value. And this p-value is associated with this null and alternative hypothesis, depending upon which set you use. So in terms of interpreting the p-value, it's very simple. So as the p-value, so we just need to state exactly what it is. It's equal to 0.000. So what that means is it's actually different to that, but to 3 decimal place accuracy, it's equal to 0. We then need to know, how do we interpret this p-value? Now what I recommend doing is what I've recommended in all my tutes, and what I've said to anyone who's talked to me about this. If you go to the summary sheet that Robert did for topic 4, so if you just go to learning resources on the Blackboard page and go to the lecture material, you'll be able to find this very easily. We then have a table within here about interpreting the p-value in general. So in this case here, remember our p-value is 0.000, so we have something which is less than 1%, so we have very strong evidence against the null hypothesis. So that's all I'm going to type. We have very strong evidence against the null hypothesis. And so, as such, we will accept the alternative, sorry about that, hypothesis. Okay, so we've given like the statistician's result in terms of, the p-value is equal to this. We're going to be accepting the alternative hypothesis, but what does that actually translate to? So remember that what we're testing is to see whether one mean difference is different from the others. So in this case, we have found that there's very strong evidence against the null. So the null is that all the means are equal. So therefore, there is at least one mean difference that is different from the other. So another way of writing that out would just be, consequently, the mean diff is affected, the mean diff is different for different colors. You could have written that there is a relationship as well between that, and it's coming up with that because I think it's under American English, so we'll just forget about that. Okay, so consequently the mean difference is different for different colors. So I know that's a pretty ambiguous sentence now that I've read it, but basically what we're looking at is this difference here. When we separate it out based upon the colors, when we find the mean for those different colors, we found that there is a strong difference. So there is a strong difference between the colors, and so therefore it's showing that there is a relationship based upon equality of the means. Okay, so that's the first thing that we need to talk about. The second thing that we need to talk about is the R-squared adjusted. And what I've done here is I've just included almost like a default response, like a template response where you could include the values within it. But just to give you a bit of an explanation of exactly what the R-squared adjusted means. So we got the R-squared here. So we got R-squared and we got the R-squared adjusted. Essentially, and this is a very, very loose definition of R-squared, the way that I like to think of it is it's the ratio of how close the model is to the actual observed data. So if the model is able to generate the observed data perfectly, then we would see that there would be an absolute 100% match, and we would have an R-squared value of 100%. If, however, the R-squared is incredibly low, like just say the R-squared was like 0, for instance, then that would mean that the model isn't predicting any of the data. So it's a measure essentially of how good it's performing. And in this case here, there's two different R-squareds. So we've got the R-squared on its own and then the R-squared adjusted. And then there's also the R-squared predicted. I'm going to use just these two values, the R-squared and the R-squared adjusted, because that's mainly what we focus on in this unit. Also too, I'm using Minitab 17. I don't know if I mentioned that earlier. And so you may not be getting this R-squared pred or predicted as well. If you don't have that in your output, that's fine. If you just have these, that's perfectly fine, because you only need to talk about these. Okay. Now the R-squared, as I was saying before, essentially what we've done in terms of this test is we've tried to define a model in which we're measuring the difference based upon the different colors. Now, essentially when you're performing any statistical analysis, in this case we're only measuring the relationship, the response, and we've only got one predictor in this case, which is being the color. Now, if you include another variable into the mix, in terms of measuring the performance, the worst it can do is give you no extra value. So what I mean by that is, let's just say we went from just including color and we add a packet into it. The worst thing that the packet can do to the R-squared value is it can just contribute nothing. So it can just have no change whatsoever. It can never reduce the R-squared value. Or, sorry, it can in some special cases. But either way, obviously, whenever you're investigating a relationship between two variables, you're investigating two variables that are isolated from millions of variables that exist out there in the real world. And the concept is, if you were to, the more and more of those variables, like every possible variable that can exist in the world, as closer and closer as that gets to being the true amount, the higher this R-squared value will incur, or the higher this R-squared value will become. Because if you think about it, like if you have some system and you include every possible variable that's associated with that, you'll have a very, very strong R-squared value because you're considering every possible relationship. That's obviously not the goal of stats. The goal of stats is not to have a model that has millions of variables that doesn't really tell us a lot. It's about isolating the key variables so that we can explain, say like, okay, what I mean by that is, let's just say we have a model where we have a response variable and we have 4 predictor variables, and that gives us 90%. Now, if I went from having 4 variables to 1,000,000 variables, and it only went from 90% to 91%, yes, it's increased and it's done better, but really overall, it's obviously a very poor modeling strategy. So, the way in which we can get over the possible errors that come into interpreting the R-squared value, which means that if you have a lot of variables, the R-squared value can be misleading. So you have 1,000,000 variables at that gives you like 90%. That doesn't make it relative to the total number of variables that you've got within it. So that if you do want to make it relative to the total amount of variables, so that when you do a comparison between a model with 4 variables and a comparison between a model with 1,000,000 variables, if you scale both of those so that the number of variables are taken into account, then you can compare the R-squared values directly. So we're going to look at this R-squared adjusted, and we see that we've got 27.49%. So here we see, as I said, we can just use this tablet from the R-squared value about, so what was it, 20, I'll just have it roughly 24%. 24%, about 24% of the variation in the response variable. So in this case, what's our response variable? That is diff. So variation, and when they're talking about the variation, they're talking about the variation or the difference between the observed data, so the data that's been recorded, and the model's data. So the variation in the diff is being explained by the different, and in this case here, that is the different colors. Okay, so this is important, and this is a big thing too, because obviously the closer this is to 100%, the better the model is actually performing overall. So even though, based upon this p-value, we have found there's a relationship, the test that we've used to find the relationship has only really found 24% of the actual data that's being explained by the model, so it's not really that great. Okay, the next thing that we need to talk about is the assumptions of the test. We've got 3 assumptions that must be satisfied, and you might be wondering, well, why do we care as much about these assumptions? If these assumptions are not met, then the results of this One-Way Anova are not necessarily incorrect, but I certainly wouldn't bet any money on them. The only way that you can be really confident in these results is if all of these assumptions, especially the third one, is satisfied. So the first one is we've got the normal probability plot, and so that comes from this graph that I had generated before here. Now yours will probably look a little bit different. As I said, I think they changed a few things around in Minitab 17. You'll see that the line here, which is probably blue on yours, is red on mine, and the dots are blue, whereas on yours they'll be red. So just keep that in mind. Don't freak out if you see this and you think yours is different. They must have just made some changes, or maybe I accidentally changed something in the options. So what I'm going to do is we're going to send this graph to Microsoft Word. So what we have within here, so as the assumption that we talked about before, so like right as we were declaring this, so before we actually went into actually analyzing the test, it says a one-way Anova assumes each of the factors levels are normally distributed with equal variances. So this is the key thing that we're looking at in terms of the normally distributed. So in order to be able to identify that, we need to have the residuals being normally distributed. Now, without going into too much detail, essentially, the way that you can identify that is this red line refers to a perfectly normally distributed situation. These dots refer to the actual data that's observed. So the closer these dots are to that line, the better it is at being normally distributed. So what we see here is we've got a pretty good overall. There is a little bit of variation, but not a great deal amount. We have got a little bit of a loose tail off here and here, but thankfully they don't account for a great deal of values. So the way that I would interpret this is the values are the residuals, so the majority of the residuals are fitted, or don't use the word fitted, sorry, positioned on the normal probability line, you could write it out as, with only a few residuals deviating away from the line. So in this situation, you need to make an assessment yourself as to, because there is, unfortunately, we don't give you a formula of, how do you exactly identify it. This is like a visual interpretation, but how do you exactly identify it? The response to that is there are formal tests for it. So there are formal statistical tests to identify if the residuals are normally distributed, but they're not covered in this unit. So you just need to make a judgment call. In this case, I'm going to say that it is. So therefore, the assumption, sorry about this, some of normality of residuals is satisfied. Okay, so we've gone through the first test, or the first assumption, and we've identified that that has been satisfied. The next thing that we need to look at is scattering of the residuals versus the fitted lines. So let's just make some space, and this is going to go on to the next page, so I may as well do that now. Okay, so in terms of how we get that graph, that refers to the residuals versus the fits for the different values. So we're going to right click, we're going to send this send graph to Microsoft Word, and see we've got it within here. So scattering of the residuals. So essentially what we want to see within here is we want to see these values to be randomly distributed. If we identify any pattern whatsoever, then what we're going to see, so what we're going to usually find is some of the assumptions are not satisfied. So like for instance, you know, the other big one, and this sort of goes over two tests, is that where am I? Sorry. So the three assumptions, yeah, the normal probability plot, but sorry, here we go, I just remembered here. Are normally distributed with equal variances. So this is the key thing that we're looking at now, is testing that assumption of equal variances. And there are two ways of identifying it. We are actually going to go into a formal test for it. But when we're looking at this visually, the reason why we do this as opposed to just doing the test is we can sometimes identify how it's been satisfied or how it hasn't been satisfied. So you'll be probably wondering why the clumps are sort of going like this. And the reason why we've got them into clumps like this, I can't say 100%, but I'm 99.99% sure, is these refer to the different colors. So blue, whatever, I can't remember, blue, yellow, white, etc. Now what we want to see is how close these are to each other. If they each have equal variances, then what we should expect to see is that each of these should have the same sort of distribution. So another way of identifying that is just to see how random it is. So what I see within here is these two seem to be similar and these two seem to be similar. Yes, there is difference within it, but in terms of the overall range, they appear to be relatively similar, and that's a bad thing. That means that there is evidence to suggest that the assumption of equal variances may not be satisfied. I think these two have equal variances, and I think those two have equal variances, but overall, do I think they all have equal variances? From that graph, I don't think so. So unfortunately, in this case, I don't think that the condition has been satisfied. So you could, you know, as seen in, you should probably have this in the first one, figure ... so label these figure 1, figure 2. So let's just call this figure 2. The residuals appear to have similar plots for coupled colors. So what I mean by that is this is a couple and this is a couple for coupled colors. As a result, the assumption of equal, so similar, yeah, actually I should include have similar plots for coupled colors that are different from each other. So if you're reading this and you're not sure what I mean by that, residuals have similar plots for coupled colors. So this is coupled, this is coupled. I think they have similar variances, but these couples are different. So this, in terms of this couple, it looks to be very different from that, so that are different from each other. That's what I mean by that. Therefore, the assumption of equal variances may not be satisfied. So this is just a visual analysis. What we actually want to have is a formal test in this case. Because this, like I know in this, you might be going, well, why have we got a formal test for this case and not for the others? This assumption here of normality of the residuals is nowhere near as big as the equality of variances. If you don't satisfy this, then essentially the results of the test are not useless, but as I said, I would be very, very careful about using those results, especially if it involved, you know, all the consequences of getting it wrong were, you know, quite dubious, like losing a lot of money, or someone goes to jail, or someone dies, or something like that. So this one definitely has to be satisfied. So when we say equality of the variances, that just means essentially like what we were testing before, where we were looking at the means. One assumption is that the variances must be equal as well. So in order for us to be able to do this, I'm just going to put this onto a new page because I know the graph will want to be on a new page. We want to test this set of assumptions, the null being that the variances are equal and the alternative being at least one is different. So we can do this test. So I'm just going to kill these. We don't need these anymore. We go to stat ANOVA test for equal variances. I know this definitely looks different to Minitab 16, so don't worry, this still exists. We go into here. The response in this case is diff, and the factors is, in this case, we're looking at color. So click OK. So this is the thing that we're interested in. And what I'm going to do is I'm going to send this graph to Microsoft Word. Okay. So what we want to see within here, and this, I think there might be something wrong with the graphics here, because what should exist is there should be dots on each of these. So if you're doing this at home, there should be dots on each of these. These refer to the confidence intervals for the actual confidence intervals for the variances. So we get the, when we, you know how in a couple of weeks ago when we were dealing with confidence intervals for proportions, it would be, okay, we've got a proportion from a sample, can we use that to estimate where the population proportion lies within? These confidence intervals can be interpreted the same way. The dots refer to the variances of the sample data, and then these intervals refer to the confidence intervals that we are confident that the true population standard deviation lies within. Anyway, the key thing that we're looking at here though is this p-value here. So we've got a p-value 0.015. So as the p-value, oh, and sorry, I know that when you're doing this in Minitab 16 and before, there's Bartlett's test above this. Don't worry about that. All we're interested in is Levene's test. So as the p-value, in this case I'll just write this way, Levene's is equal to 0.015, so 1.5%. Okay, we're not sure about what we can do within here. So we've got 1.5%, so we're between 1% and 3%. We have strong evidence against the null hypothesis. We have strong evidence against the null hypothesis. Okay, so now that we have very strong evidence against the null hypothesis, what does that mean? Therefore, that means at least one of the variances is different. As a result, the tests, or should I say, the variances do not appear. So maybe we should write it this way: the variances of the diff do not appear to be equal for each of the levels. So for each of the factors, levels, or that could be written as, say, each of the colors. Isn't that, you know, just a really poor victim of our of English? Colors can earn colors, and anyway. So unfortunately what we found is this assumption here has not been satisfied, and notice here we seem to have the relationship that we see within here. These two obviously refer to these two, and these two bars obviously refer to that. So the suspicion that we had before that they weren't equal has been satisfied. So we can see it within here, within that test. So now what we need to do is we just need to have a summary of the three assumptions which have been satisfied, which haven't been satisfied, and then how confident we are in the results of this. So the only assumption, yes, and this can be really bland. The assumption of normality of residuals was satisfied. However, the assumption of equal variances was found to be violated. As a result, we must treat the results of this test with with caution. That's all it's saying. And that's it. So I know that this video has gone really long, and so I'm going to leave it there. As I said, it's a relatively simple process to go through. I'm sure you'll be able to look at your data for your group project and identify situations in which you can do this. So I'm just gonna end this video now. I'm gonna put it up onto YouTube and send it over. If you've got any questions whatsoever, please comment on the page or send me an email at dp_galia@hotmail.com, and I'll do my best to get back to you as quick as I can. Okay guys, thanks for that. Bye.